So here we go with GCSE Physics from CCEA, Unit 1, 2018. This is the new specification. 1A. Two cars take part in a race over a distance of 500 meters. The time starts when car A passes the start line. Car B is given a penalty and waits 2 seconds before it can pass the start line. The distance time graphs for both cars are shown below. So we've got this with car A starting and car B starting 2 seconds later. How far ahead of car A is car B when it wins the race? Okay, let's have a look at this graph again then. So the race is run here at 500 meters, and at that point, at the same time, car A is at 400 meters, so it's 100 meters behind. At what time does car B overtake car A? Well, that'll be when they're at the same distance, and they're at the same distance here. That corresponds to 5 seconds. Part 3. Calculate the average speed of car B from the time it starts to move. Show clearly your calculations, starting with the equation you plan to use to get your answer. So, average speed here would be total distance over total time. And we've got a total distance of 500 meters for car B and a total time of 12 seconds. So we've got 512, and that gives us 41.7 meters per second. Part 4. On the grid opposite, draw the distance time graph for car A if it is to travel at a constant speed and win the race 1 second ahead of car B. Right, let's look at this graph again. And so we have to go at a steady speed and win 1 second ahead of car B, which means we need to end up at our 500 meters 1 second before, 11 seconds. So we need a straight line for car A that reaches that point. And that looks something like that. Part B. A ball is accelerating down a slope several meters long. The slope has markings on its surface 1 meter apart. Describe how you would use a stop clock to show that the ball is accelerating. So if the ball's heading down here and it's getting faster, then crossing one of the early 1 meter gaps is going to take a longer time than crossing one of the later 1 meter gaps. So you would need to do 2 separate experiments, one where you're timing an early one where you're timing a later one. So something explaining that you need to time it over the top gap and then run it the whole way down again, but only time over the bottom gap. If it's really accelerating, you would expect the second time to be shorter. You need to be clear that you're timing it even though it's running from the top both times. If you were to actually just lower the ball and run it over the bottom gap, you'd probably get the same time. So it has to be running all the way down the hill. It's just where you're timing it that changes. What would you do to improve the reliability of any measurements? Well, the issue here is going to be the person starting and stopping the watch. And so when you do that, the easiest way to eliminate errors in the person starting and stopping the watch is to repeat and average. Part C. A car approaches a set of traffic lights just as they change from green to red. The graph below shows how the velocity of the car changes as the driver brakes and brings the car to a stop. How long does it take the driver to react to the change in the traffic lights? Okay, so you can see here that there is no change in the motion of the car, and that will be the time it takes from him noticing the light to pressing the brake. So he or she will take a time to react here before the brake pedal is pressed. And so the answer there is 1 second. Part 2. Using the graph, calculate the distance the car travels from the moment it starts to slow until it stops. Show clearly your calculations, starting with the equation you plan to use to get your answer. So let's have a look at this graph again. So from the moment it starts to slow, well, that's from here. And to get the distance travelled from velocity time graph, we need the area. So we need to break this into zones. So A, B, C. And we need to state that we're finding the total area. The distance is the area under the graph, which is A plus B plus C. We just need to fill in some expressions for those. So A is a triangle. It's 1 second wide and 8 seconds tall, so it's a half times the base times the height. And we're adding that to B, and B is just a rectangle that's 1 wide and 4 tall. Adding that to C, and C is 3 wide and 4 tall, so it's a half times 3 times 4. So the first bit there comes to 4, the second bit there comes to 4, the third bit there comes to 6, so that is a total of 14. Part 3. The car did not accelerate at a constant rate. Explain how the graph shows this. Well, decelerated at a constant rate. It has two different gradients. A constant deceleration should be a single straight line. Part D. A car starts from rest and accelerates uniformly, reaching a velocity of 28 meters per second after travelling 70 meters. Calculate the following. At each step, you should show clearly your calculations, starting with the equation you plan to use to get your answer. So first of all, the average velocity of the car. Now, when a car accelerates uniformly, you're allowed to use u plus v over 2 for average velocity. And so that's just going to give you 14 meters per second. Time it takes the car to travel 70 meters. Well, now that we have an average velocity, we can use that together with the distance to get a time. So total distance divided by average velocity will give you the time taken. Uh, 70 over 14, that comes to 5 seconds. Calculate the acceleration of the car during this time. Well, now that we have a time, A can be just written as v minus u over t. So that's like 28 minus 0 divided by 5. And that comes to 5.6 meters per second squared. To A, the diagram shows a car moving along a straight level road. The arrows show two horizontal forces acting on the car. The mass of the car is 750 kilograms. So we've got a forward force from the engine of 1250, and we've got resistance forces of 250 newtons. Calculate the acceleration of the car. Show clearly the calculation starting with the equation you plan to use to get your answer. So this is Newton's second law. So we've got the resultant force equals ma, and the resultant force here is going to be 1250 minus 250, and that's going to be equal to 750 times A. So A is going to be like 1000 over 750, which is like 1 1/3. Part 3. After a journey along the motorway and with the same forces acting as above, it is found that the acceleration is now greater than the value calculated in part 1. Give a reason for this. Well, what is causing it to accelerate? Well, if we assume those forces are the same, the forward and backward force, the engine pulls just as much and the air resists just as much. The only thing that could be changing here, possibly, would be the mass of the car, because you would have used up fuel. So if this bottom line decreases, this answer is going to get bigger. So if the mass decreases when you use up fuel, then the acceleration would increase. Part B. To investigate how the acceleration of a trolley depended on the mass of the trolley, the apparatus shown below was set up. The trolley was pulled along by a constant force. The acceleration was measured using a light gate connected to a computer. And so we've got a single light gate double interrupt card here, which does allow you to find accelerations The first bit of the card going through, the second bit of the card going through gives you two velocities, and it can then work out an acceleration based on how much those velocities have changed. So this is a valid setup for finding accelerations. The results are shown. You've got various masses of the trolley, and you get various accelerations. And that relates again to that last part we were doing, where the mass changing at a constant force would alter the acceleration. So when the mass was low, you get high accelerations, and when the mass was high, you get low accelerations. On the grid opposite, plot a graph of the mass of the trolley on the x-axis and the acceleration on the y-axis. Draw a curve of best fit through the points. So I brought these results forward so that we can see what we're doing, and we need to plot those now. Obviously we need to set up a scale as well based on what these numbers go to. So we've got acceleration in meters per second squared, mass in kilograms. So looking at the numbers, we need a mass that goes all the way to 3 and acceleration that goes to at least 1.2. So we can make this like 0.5, this 1, and this 1.5. And mass, we could go 1, 2, 3. I'm sorry, this is a bit of a mess, but I can't really undo very well here on the iPad at this stage. So we need to plot these points. Half a kilogram is here, 1.2 is like there. 1 kilogram and 0.6, so 1 kilogram, 0.6. 1.5 kilograms and 0.4, so 1.5 kilograms, 0.4, and 2 kilograms, 0.3, 2 kilograms, 0.3 is going to be like there, and finally 3 kilograms and 0.2, so 3 kilograms and 0.2 is going to be there. And now we have to plot a curve through those. So we end up with something like that. So last of all, we're asked, which one of the following equations is the correct relationship between the acceleration of a trolley and its mass m? Well, this is Newton's second law, which is F equals ma, and F is a constant. So it is going to be this one, because F equals ma and F is constant in this experiment. So we've got a constant equal to ma. Part C is Hooke's law. Question: 3 identical springs are suspended from a beam and various weights are added as shown in the diagram below. Using the information from the diagram, calculate the unextended length L of the spring when no weights are attached. So what you want to notice here is that between here and here we've got F of 1 Newton causing an extension of 4 centimeters. So if we remove F, we would expect it also to go back 4 centimeters. So the unextended length is going to be that middle length, 10 minus 4, which gives you 6 centimeters. Calculate the spring constant for the spring shown and state its unit. Again, we already have values for this. We've got a force of 1 causing an extension of 4. And so F equals Ke. K would just equal F over E, which is 1 over 4, which is 0.25. And we're dividing newtons by centimetres, so it's going to be in newtons per centimetre. Remember, units come from what you were doing, and what we were doing was dividing 1 newton by 4 centimetres. So this is newtons divided by centimetres. Using your answer to part 2, calculate the force needed to give the spring an extension of 10 centimetres. So what we do here is we bring that K down, and we use it in conjunction with that extension of 10. and we just fill in our Hooke's law equation. So F equals KE is going to be 0.25 times 10, which is going to give us 2.5. So we get 2.5 newtons for that. Part D is a basic moments problem. The diagram below shows a simple pressure relief valve. When the steam pressure reaches a certain value, the valve opens to reduce the steam pressure. Using the principle of moments, calculate the size of the upward force exerted by the steam, which will open the valve. Show clearly your calculation, stating the equation you plan to use to get your answer. So this is straightforward principle of moments, that the total clockwise moment equals the total anti-clockwise moment. Just need to be very careful here, because while the steam force is 5 centimeters from that pivot, because let's face it, the pivot is here. This is the pivot here. And that steam force is 5 centimeters from that pivot. The 25 newtons is not 30 centimeters. So the most common error is people to just copy that 30 into their equation. And that's the difference between an equation robot and someone who actually knows what they're doing, because that is 35 centimeters to the pivot. Remember, the moment of a force is the force times its perpendicular distance from the pivot. So you should always be thinking about doing that, or indeed redrawing the problem with only the distances that you're interested in. So you've got an upward force there at 5, you get a downward force there at 35. So sometimes redrawing the diagram helps you to not make a mistake when you're doing your moments problem. So if I've got a pivot there, then the anti-clockwise moment about that pivot has to equal the clockwise moment about that pivot, and you can also write that as ACM equal to CM if you wanted. And the anti-clockwise moment is the steam force times the 5. That's the thing trying to turn it anti-clockwise. And the clockwise moment is the 25 newtons times the 35 centimeters that it is from the pivot. And then we just solve that. F's going to be 25 times 35 over 5. And that comes out to be 175 newtons. At another time, the pressure of the steam was 36 newtons per centimeter squared. The area that the steam pressure acts on is 5 centimeters squared. Calculate the force exerted on the valve. Okay, so this is the pressure equals force over area, and in this case it's force equal to pressure times area, which in our case is 36 times 5, and that gives you 180 newtons. Part 3. A student was asked to find the density of a liquid using the apparatus shown below. However, the student writes down the measurements but does not record them in an organised way as shown below. So you've got 50 centimeters cubed, 125 grams, 85 grams, 40 grams. Place the measurements on the correct line below. One has been done for you. Okay, so we've got two of these that are masses, one that's a volume. So the volume has to be the 50 centimeters cubed. So the one that says volume has to be the 50 centimeters cubed. The measuring cylinder and the liquid has to have a greater mass than that of just the measuring cylinder. So if the measuring cylinder is 85, then the higher mass has to be the cylinder plus liquid. So that has to be the 125, and then the liquid on its own has to be the 40. Using your measurements above, calculate the density of the liquid. Include the unit for the density of the liquid in your answer. So density is mass over volume, and that equals the mass of the liquid divided by the volume of the liquid, which is the 40 over the 50. I'm just realizing I didn't put units on those. Okay, and that's going to be 0.8. and that's going to be, we divided grams by centimetre cubed, so that's going to be grams per centimetre cubed. State how the student should accurately read the volume of water in the measuring cylinder. Okay, so there's several things you're meant to do. 1. Place it on a flat surface. 2. Get your eye level with the water. And 3. Read to the bottom of the meniscus. Part B. Use kinetic theory to describe carefully the difference between the motion of the molecules in water and glass. So this is basically, can you describe the difference between the motion of molecules in a liquid and a solid? So molecules can move past each other in a liquid, that's why it takes up the shape of the container, it can't hold its own shape. And in a solid like glass, the molecules vibrate about fixed positions, that's why it does have a definite shape. Part C, a fixed mass of water was heated and the density of the water was measured at different temperatures. The results of the investigation are shown in this graph, and you can see density is rising between 0 and 4 degrees and falling between 4 and 80 degrees. Describe how the volume of the water changes. So remember that density is mass over volume. So if density is rising, volume is decreasing, and if density is falling, volume is increasing. So density is rising from 0 to 4, so volume is decreasing. And from 4 to 80, density is falling, so volume must be increasing. So the important thing here is to remember that your equation is your friend, helping you to figure this out, and you should answer the question. I've seen lots of examples where people talked about things here that weren't the volume. If they specifically ask you to talk about the volume, then whatever you say next must be about the volume. 4a. Describe in detail how you would measure the personal power of a student by having the student climb a staircase or perform step-ups on a platform. The weight of the student is known. Okay, so you don't have to measure the weight of the student. Climbing the stairs is a fairly common one here, so we'll do that. What apparatus would you use? Well, we need to know how long it took them to go up the stairs and what height those stairs are. So we'd need apparatus for measuring those two things. So you've got a stopwatch to time the journey, and you need a tape measure to measure the height of the stairs. So what about these measurements? So use the tape measure to measure the vertical height of the stairs first. So you need to explain it. You're starting the stopwatch as they begin to climb the stairs, and you're stopping it when they reach the top. And then you're recording these results. So in the calculation, you need to explain with your equations what you're doing with these numbers. So their power is the work done of the time taken. And so the work done can be represented by their weight times the height of the stairs. So we multiply their weight in newtons by the height that they climbed to get their work done. We then divide the work by the time taken to get their personal power. Part B. Below is a list of energy resources. Indicate which are renewable and which are non-renewable by placing a tick in the appropriate box. The first one has been done for you. Coal is non-renewable. Tidal power, well, there's tides every day, so it's definitely renewable. Biomass, well, you can grow more crops and turn them into something to use, so it is definitely renewable. Wind, well, there'll be new wind every day because of the sun heating the earth. Nuclear power, well, that's based on uranium dug up in the ground, and so that is non-renewable because that uranium will eventually run out. A student uses her mobile phone. Complete the energy flow diagram for the mobile phone. Write the form of energy in the spaces provided. So we've got obviously chemical energy in the battery, that gets converted to electrical, and then the electrical coming out of the battery, the phone turns that into, well, the screen will light up, the phone will make a sound, and any electrical device will make heat. So we have a straight example of filling in an equation here. For every 240 joules of input energy to a food blender, 144 joules of useful kinetic energy are produced. calculate the efficiency of the blender. So this is just use of the efficiency equation. The efficiency is useful output energy over total input energy, which in this case is going to be 144 over 240. And that gives us 0.6. And we remember here that efficiencies don't have units because the top thing and the bottom thing, when they're divided, the units cancel. Part E. A carriage is at the top of a roller coaster track 40 metres above the ground. The mass of the carriage and passengers is 1200 kilograms. Calculate the potential energy of the carriage and passengers. Show clearly your calculations, starting with the equation you plan to use to get your answer. So this is like gravitational potential energy is mgh, and then we're just filling that in. So GPE equals mgh, 1200 kilograms times 10 for g times 40 for h gives you 480,000 joules. Part 2. At the bottom of the slope, the carriage and passengers have a total kinetic energy of 2.4 times 10 to the 5 joules. Show that its velocity is 20 meters per second. So again, this is straight substitution into a kinetic energy equation. The kinetic energy is a half mv squared, and then you're just rearranging that for v. So we've got kinetic energy is a half mv squared, multiply by 2 to get rid of this half, and you get 2 times the ke is a mv squared. Divide by m to get rid of this m. 2 ke over m is v squared, and then finally taking the square root of 2 ke over m is v. So now we need to substitute into that. So v is going to be the root of 2 times the kinetic energy over the mass, so 2 times 2.4 times 10 to the 5 over 1200, and then take the root of that, and we find that that is indeed 20 meters per second. Part 3 then, when the brakes are applied, the carriage comes to rest in 30 meters. Calculate the friction force provided by the brakes. So we've got a kinetic energy, we've got a force, we've got a distance. So this is like the work done by the brakes using up all the kinetic energy. So the loss of kinetic is equal to the work done by the brakes. In other words, that 2.4 times 10 to the 5 is how much it loses. That's equal to a force times a distance, where the distance is how long the car travels before it stops. And then we just divide both sides by 30 to get an expression for F. And that gives us F equal to 8,000 newtons. Part F, the thermal conduction by copper and glass can be compared using a computer and the apparatus shown below. The glass and copper rods are of equal length and diameter, and you can see they've got temperature sensors going into them, and then they're in hot water. By using the axes below, sketch 2 graphs that would be obtained, one for the copper, one for the glass. Label each graph. So the copper is a conductor, and obviously it's going to heat up quicker, and the glass is an insulator, it's going to take longer to heat up. So the temperature measured by the sensors is the same until the very hot water is poured into the tank. So we want 2 graphs with the copper rising quicker and the glass rising more slowly. So we get something like this. Remember, they're heading towards whatever temperature that water is, so they will be leveling off, so they'll curve this way, but the copper will increase quicker to that, and the glass will still be curving towards that, but take much longer. Part 2, describe the role that particles play in the conduction of heat by copper. So here we're talking about free electrons because copper is a metal, and we need to explain how they pick up heat at the hot end and race around inside the copper, transferring that heat by collisions with ions elsewhere in the copper. (5a) An experiment was completed to measure the half-life of a radioactive source. The corrected count rate in counts per second was recorded at set time intervals and used to plot a decay graph as shown below. Use the graph to find a value for the half-life of the radioactive source. You're advised to show clearly how you get your answer. So firstly, we note that it starts here at 500, and then we want to look at when it halves, and so we're looking at the time taken for it to reach 250, so that's the first point we would mark on the graph. And you can see that's about an hour and a half. So we could go again and try and go from 250 to 125, and you can see that also takes about an hour and a half. And we could go for some third arbitrary time if we were really pushing it. We can see up here it goes to 300. So we could maybe make a mark there and then look again at 150. And that one's taking about 1.4 hours. So that's three values we've got. So we just take an average of those three. And that comes out to be about 1.47 of an hour. Part B, radioactivity is used in industry to control the thickness of aluminium sheet. You can see here we've got this control unit which basically squeezes the rollers, and then we've got a source and a detector. So you've got like a radioactive source here being detected by the detector, and that's controlling how much squashing there is. So the thickness of the metal is determining how much of the radiation gets through, and how much of the radiation gets through is then squeezing the rollers to make sure that they maintain a specific thickness. Discuss the properties of the radioactive source and how it is used to control the thickness of the aluminium. So this is done in like three parts. It said in your discussion you should state the type of radiation, alpha, beta or gamma, used, giving a reason for your choice, and then explain why the half-life of the source is an important issue with in the choice of the radioactive source, and then describe how the count rate measured by the detector is used then to control the thickness of the aluminium sheet. Okay, and you'll be assessed on your written communications here. So the radioactive source we would need, well, alphas won't go through aluminium, and if it's thin aluminium like foil, then it might not change very much when you put gammas through it. The signal might not decrease by much, so you probably have to pick betas for this. So you just give a reason why you're picking them, so alphas wouldn't pass through it, and the gamma value might not change much when the thickness of aluminium changes. So that's good enough reason to pick betas. We're then asked to explain how the half-life of the source would affect the choice of the material that you use, the radioactive material. And if you think about it, if this has a low half-life, then its counts per second are going to be decreasing over time, and that's going to result in the machine reading lower and lower values, and that may cause it to set the wrong thickness. So you would need something that has a fairly constant count rate coming from it, and that would mean something with a fairly long half-life. So you just explain you would need a long half-life, and because you would need a steady count rate over the life of the machine, otherwise the machine would need constant recalibration to avoid the metal getting progressively thicker. Sorry, I'll just fix that. So then the last bit, you're meant to explain how they can use this to control the thickness. And so you just explain that the count rate is relating to how many beta particles are getting through to the detector. If too few get through, then the roller pressure is increased, causing the metal to exit thinner and the count rate to increase again. So the thickness then can be adjusted, and the count rate will then return to some value that you're expecting. And the idea is that you let pressure off the rollers or push on the rollers to adjust that. Part C, the diagram shows what happens when a heavy nucleus undergoes fission. Label the particles involved. Okay, so the particles here would be, the big one's going to be uranium, and how we get it to split is to hit it with a neutron. So the big particle is uranium, the little particle is a neutron. So this fission reaction releases energy. What form does this energy take? Well, if you remember, what's going on here is that these particles all fly apart. And if this is happening within a solid, then they're thumping into their neighbours. So it basically comes out as the kinetic energy of these particles, which basically then turns into heat. So it comes out as the kinetic energy of the fragments, which basically then makes heat. Describe the role the particles above play in the chain reaction. Now remember, the chain reaction is where the neutrons from the first fission go on to hit other uraniums and cause further fissions. So you're just explaining the idea that neutrons released in the reaction will go on and hit other uranium at nuclei. So just something explaining that. Part D, nuclear fusion has the potential to provide very large amounts of energy. It is possible to fuse isotopes of hydrogen to produce another nucleus and release a lot of energy. The diagram below shows a fusion reaction involving isotopes of hydrogen. Write the names of the isotopes in the boxes provided. So your specification says that you're supposed to know that isotopes of hydrogen are called deuterium and tritium. So it's worth making sure that you have learnt. And deuterium is the one with 2 particles, and tritium is the one with 3 particles. And we have reached that magical bit where it says this. Thanks for watching.